Kuzangpo. Welcome to Bhutan e-learning program. I'm Khaganath Gajmer from Dampu Central School. In today's lesson, I'll be discussing about one of the analytical technique, which is mass spectroscopy. This mass spectroscopy is one of the most important technique which is being widely used in the analysis and identification of various chemical compounds in different fields. This spectroscopy is basically used for identifying the molecular mass of a given compound. Now, in today's lesson, under mass spectroscopy, we will be discussing the principle of mass spectroscopy. We'll also illustrate the mass spectrum of certain compounds. We'll also explain the instrumentation of this mass spectroscopy. We'll also try to see some of the applications of mass spectroscopy. Now, mass spectroscopy is an analytical technique in which the sample of a chemical compound is converted into gaseous positive ions by bombarding it with the help of energetic electrons. Now, here in mass spectroscopy, what is being done is the sample of a chemical compound is taken here, and then this compound is being bombarded with highly energetic electrons, and when electrons bombard this molecule, these electrons will liberate, the electrons from this molecule will be ejected, and then the two electrons will come out, one electron from the bombarding electron, which comes from bombarding electron, and another electron from this particular compound or molecule will be ejected. So, in total 2 electrons will be released. So, during the bombardment, what happens is this molecule gets ionized. It becomes molecular ion now. It becomes positively charged with 1 electron less. So, this is called now molecular ion. Now, this molecular ion now will further undergo fragmentation to form different other smaller ions, which are called daughter ions. So, from molecular ion, first from molecule to molecular ions, and from molecular ion again further fragmentation, it will form the fragmented ions, which are also positively charged. So, what is being done is these fragments are now being analyzed by the instrument called mass spectrometer. So, the fragments are analyzed based on their mass is to charge ratio. Now, the purpose of this mass spectroscopy is basically to find the composition of a given compound and also to elucidate its structure. Now, from the mass spectrum, we can identify the composition and also we can draw the structure of the given compound of any chemical compound. Now, let us look at the principle. As I said earlier, as I discussed earlier, the molecules are in the principle involved in this spectroscopy is the molecules are bombarded with an energetic electrons to produce positively charged ions called molecular ions. The molecular ions are further fragmented into stepwise manner to produce smaller ions called fragmented ions or daughter ions. Now, each kind of the molecular ions or the fragmented ions has certain mass to charge ratio. These fragmented ions have certain mass to charge ratio. Now, for example, let us look at the fragmentation mode of ammonia molecule. Now, we take the ammonia molecule and we bombard it with high energetic electrons, beam of electrons. Now, the molecular ammonia will undergo fragmentation in this manner. This molecular form of ammonia, which is in a molecular form, when it is being bombarded with the high energetic electron, will lose 1 electron from the molecule and then form molecular ion. Now, this molecule as a whole will have 1 positive charge, so therefore, it is called molecular ion. Now, this molecular ion will further undergo fragmentation by losing 1 more hydrogen. So, after losing one more hydrogen, it will form now NH2. Now, it has become a smaller fragment now with lesser m by z value. And further, this fragment will again undergo fragmentation to form, now one more hydrogen will be lost to form NH plus. So, another again smaller daughter fragment or daughter element or daughter molecule, which is having again lesser m by z value, which is 15 now. And finally, the last hydrogen that was attached to nitrogen will be lost to form N plus ion, which has again lesser m by z value. Here, the molecular ion m by z value is 17, because the molecular mass of this ammonia molecule is actually 17, and the charge that it has is 1. Therefore, 17 divided by 1 is 17. So, therefore, here also in all of these fragments, you will have the charge which is equal to 1, positive 1. Therefore, their m by z value becomes their molecular mass. So, this is how the fragmentation of ammonia molecule takes place when it is being bombarded with the highly energetic beam of electron. Now, the most of the ions or the charge is 1, and the m by z is simply the molecular mass of the ions. That means, as I said, the charge of the ions are usually 1. So, therefore, their m by z value becomes usually their molecular mass. The positively charged ions produced are separated by passing them through the electric field and magnetic field. Whatever fragments are produced after the bombardment by the highly energetic electrons, these fragments are now passed through the electric field. Now, after passing through the electric field, they get accelerated, and then they move now next to the magnetic field. Now, in the magnetic field, then what happened is then the fragments are analyzed based on their m by z values. The intensity of each signal represents the relative abundance. Now, after that, there is a detector. Detector will detect how much of ions are produced during the fragmentation process. Now, let us look at again the ammonia. This is how the fragmentation process takes place. Now, if we look at how the fragments are being analyzed, in the first case, we have here a sample. Let us take a sample of an organic compound or any chemical compound, and this compound is now converted into gaseous form. After that, these molecules in gaseous form are bombarded by a highly energetic beam of electrons. Now, after that, fragmentation will take place. Then different fragments of ions or daughter ions will be produced, and these fragments are now passed through the electric field. Now, once they pass through the electric field, they will be accelerated. Now, they will be made to move at a higher speed towards magnetic field. Now, they will be passing through the magnetic field. We have magnetic field being placed here. Now, in the magnetic field, what happens is the different fragments with the different m by z values gets separated. Now, in the magnetic field, the one with the lower m by z value will be deflected more, and the one with the higher m by z value will be deflected less. So, this one will be deflected more, this one will be deflected less. So, depending on their m by z value. So, accordingly, the detector will detect, and then the signal will be produced, which is called mass spectrum. Like if it is a very light fragment, so it will have a greater turn. Like for example, if it is a light vehicle, if you are turning a vehicle, and if it is very light vehicle, then you can make a turning at a sharp turning. You can turn it properly at a greater angle. But if it is a heavy one, then you will have to have a turning with a lesser angle. So that's similarly here, the one with the lesser mass will have higher angle of this turning here, this deflection. So the one with the higher m by z value will have the lesser angle of the deflection. That happens in the magnetic field. Now, let us look at how the fragments are being produced and how they are being analyzed. Let us look at this. These are the fragments being produced, pass through electric field, finally to magnetic field, and then they are being detected. So, here the fragments produced are allowed to pass through the electric field. After that, they are made to pass through the magnetic field. Now, in the magnetic field, they get deflected at different angle depending on their mass. So, the detector will detect at how they are being deflected, and accordingly there will be signal produced in the computer. Let us look at the mass spectrum of ammonia molecule. Ammonia molecules, we have different fragments. So, we have fragment which is N plus, and then we have NH plus, the second fragment, and then third fragment we have this NH2 plus. The second one we have molecular ion which is NH3 plus, and we also have an ammonia molecule which is the isotope of nitrogen 15. Now, they have different M by Z value. The first one, the M by Z value is 14, 15, 16, 17. So, these are the M by Z values of different fragments, molecular ions, and the molecule itself. Now, here in the mass spectrum, the signal produced will be in this manner. Here, if you look at this side, we have M by Z values, and that side on the x-axis we have relative intensity. Now, the relative intensity will tell us how much of these fragments are being produced during the fragmentation. The quantity of the fragments are being given by the intensity of the signal. Now, here if you look at here M by Z value, the highest M by Z value that the signal is produced is at 17. So, we do not have any signal further than this. So, this is the signal having highest M by Z value. Now, this indicates that the fragment is this signal indicates that the fragment has the highest molecular mass. So, this signal can be the signal of that molecular ion. So, if we have a molecular ion, let us say 17 here, so this is the molecular ion. So, its M by Z value is 17, so its signal should be somewhere here. This is the signal with the highest M by Z value. So, the last extreme signal with the highest M by Z value will tell us about the molecular mass of the compound. So, like accordingly, we will have the other signals depending on the M by Z value. For example, this 16, the signal will be produced here, and we will have 15, 14, and so on. So, different fragments will have different signal, but the signal with the highest M by Z value will tell us that it is the signal of molecular ion, which will also give us the molecular mass of the compound. So, this is the mass spectrum of the ammonia molecule. Now, during the fragmentation, if there are any neutral particles being produced, these are not being detected by the mass spectrometer. It will be simply allowed to go as it is, unaffected. So, only those charged ions are being detected by the mass spectrometer. Now, how do we interpret when we have the spectrum of a given compound, mass spectrum of a given compound? How do we interpret that from the spectrum? How we will be able to, what are the informations that we will be able to get? So, the peak with the highest M by Z value, it is the peak of the molecular ion. So, the peak or the signal with highest M by Z value will tell us or gives us the information about the molecular mass of the compound. The peak of the molecular ion or parent ion is usually with higher intensity, and it is taken as base peak. And in the spectrum, if the signal is with higher intensity, having high intensity, meaning this fragment, particular fragment is having, it is more in number, then it will have more intensity, then that particular signal is that particular signal or the peak is called the base peak, and we take that peak as 100% evidence. The relative intensity is considered as 100%. For example, let us look at in case of ammonia. In case of ammonia, let us look at the spectrum again. Now, here in this case, this is the highest M by Z value, signal with highest M by Z value. So, this peak or the signal also will indicate the signal of that of molecular ion. Now it has, if we compare the intensity, this has the highest intensity, it is almost highest compared to others. So whichever is whichever peak or the signal is having the higher intensity, that we take it as 100% and rest are compared with it. And that peak with the higher intensity, highest intensity is called the base peak. So base peak is usually taken as 100% intense. So rest are made, rest are rate or studied as compared to with reference to the base peak. Now sometimes this, if you look at this again, sometimes this peak is also a parent peak. Parent peak means the peak with the highest m by z value, that is called parent peak. And even if the peak with the highest intensity is called the base peak. Sometimes in this case, sometimes the base peak and the parent peak are same. In this case, if you look at here, this is parent peak as well as base peak. But it is not true in all the compounds. There are some compounds in which the parent peak and the base peaks are different. For example, if you look at this compound, which is N-pentane, if you look at this compound N-pentane, now the mass spectrum of this compound is given by the spectrometer is this form. Now here we have this one, this compound, this signal at somewhere at 72. So this 72, m by z value 72. Here this signal is having the highest m by z value. So from this signal we will know that the molecular mass of the compound is 72, because this is a molecular ion, is the peak of the molecular ion, which will also tell us, also give us the information about the molecular mass of the compound. So here it is 72. Now if you look at the intensity of other signal, this base peak, another fragment is there with the molecular mass or m by z value 43. Now this 43 is having higher intensity compared to this one, parent peak. So here this is the parent peak with highest m by z value, but it is not base peak. So here this fragment 43, the fragment with m by z value 43, the fragment with m by z value 43 has the highest intensity. Therefore this fragment becomes the base peak. So this peak has the highest intensity, therefore it becomes the base peak. So here base peak and parent peaks are different. But in case of ammonia, parent peak and also the base peak are same. It is shown and indicated by just single peak. The molecular mass of the molecular ion as analyzed by the mass spectroscopy gives the molecular mass of the compound. As we have already discussed, the molecular mass of a compound can be obtained from its parent peak. The mass spectrum of a particular compound is unique, and no two compounds will have the same mass spectrum. So if we take different compounds and analyzed with mass spectrometry, then we will have a different signals for different compounds. So from there we will be able to identify a particular given compound. Mass spectrometry or mass spectroscopy is usually used for determining molecular mass of the compound from the m by z ratio of molecular ion. So here basically the important application of this mass spectroscopy is to calculate or to determine the molecular mass of a given compound. That is the important application. Other one, it is also to identify the given compound from its base peak. Now every compound will have their own base peak. So depending on the nature of this base peak, we will be able to identify the given compound. Now it is also helpful in elucidating the structure of the compound from its pattern or mode of fragmentation. Now different fragmentation, when we analyzed the compounds in a mass spectrometer, different compounds will have different mode of fragmentation. The way they undergo fragmentation will be different. So from the mode of fragmentation, we will be also able to elucidate the structure of the compounds. Now some of the features of parent peak. The molecular ion or the parent peak in aromatic compound. If we take aromatic compound, the parent peak is comparatively intense due to delocalized pi electrons. Now, if you take any aromatic compound, we will see that in mass spectrometer, their parent peaks are little bit intense, meaning having higher intensity. And unsaturated compounds with double bonds or triple bonds give more intense peak than those saturated or cyclic compounds. Now, unsaturated compounds, those compounds having double bonds or triple bonds, these compounds, they will give a slightly intense the peak or the signals compared to those unsaturated or cyclic compounds. The intensity of the peak given by the saturated compound is more than the corresponding branch chain with same number of carbon atoms. For example, the intensity of molecular ion of N-pentane is intense than that of neopentane. Now, let us look at an example. Here, this compound, the first one, this is N-pentane, which is straight chain compound. Now, with the same molecular formula, we can have this compound, which is neopentane, which is in a branched form. So, this is N-pentane and this is neopentane. This is straight chain and this is branched. Now, if you look at their mass spectrum of these two compounds, if you look at, now they will have slightly different in terms of signal and then in terms of intensity of the peaks. Now, if you look at this straight chain form, we will have parent peak will be same. They will have the parent peak at the same m by z value, that is 72, 72. So, this 72, this peak highest m by z value will tell us that the molecule has the molecular mass of 72. Now, if you look at, now they are the parent peaks of these two compounds. Now, if you look at their parent peaks, you will see that the unbranched or straight chain compound has slightly intense, intense signal here. Here the intensity is quite low here, but here it is quite high. So, that is how we distinguish the compound with same molecular formula. The intensity of the parent peak will differ. So, that is how we distinguish the given compound. Now, here the base peak, again here it is 43, again here this compound has a base peak shown by a fragment with m by z value 43, whereas in this compound the base peak is shown by that fragment with m by z value 57, even the base peaks are different. So, different compounds, different base peaks. Let us look at the mass spectrum of neopentane again. Now, from here, from the signal or the peaks or the spectrum of this neopentane, we can also write the different fragments, their formula and the molecular mass of different fragments. For example, if you have one signal here, it is somewhere at 72, highest one, m by z value highest. So, we will know that this signal is the signal of that of molecular ion. So, it can be 72. So, directly we can take. So, it is a neopentane. So, it is 72. So, this is the fragment. So, this becomes the molecular ion. So, this fragment molecular ion will give this signal at 72, m by z value 72. Now, we have another fragment with the highest intensity, and this intensity which is also giving base peak with the m by z value of 57. So, from here the fragmentation has taken place. So, the next fragment that is formed is C4H9 plus. So, if you look at its m by z value, it is 57. So, this signal or the peak is given by this fragment. And we have next one, let us say 41. 41 can be the signal or the peak of this fragment C3H5 plus. And next fragment we have 29, can be of 29, it is the peak of this fragment, and finally we have 27, which is the fragment of, the peak of this fragment. So, from here, so these are the different formula of the fragments. So, molecular ion, and these are called daughter ions, which are fragmented ions. So, from here, this particular fragment gives the base peak with the highest intensity. Now, if you have known how to write the fragments and their formula from the spectrum, then you can try this. You can write the fragmentation of N-pentane. So this is how we write. If you have to write the fragmentation mode of N-pentane, from this again, from this spectrum, we can also deduce the different fragments and their formula. So from here, so this is the base peak shown by a fragment with m by z value 43. So this becomes the base peak. So these are the different fragments. This is the molecular ion. So molecular ion peak is given here, and rest are the peaks or signals of these fragments, depending on their m by z value. Now, in case of chloro and bromo compounds, isotope peaks along with molecular ion peak or parent peak are also formed. Now, if you look at the, let's say, bromo compound, let's take ethyl bromide. In ethyl bromide, the bromine in the molecule can be of two. It can have two types of isotope. One isotope can be with atomic mass of 108. Then next isotope that we can have is bromine atom with atomic mass of 110. So we have 108 here, so 110 here. So this compound, particular ethyl bromide, can have bromine in it with different, in the isotopic form of bromine will be there in this compound with different molecular mass. Now, atomic mass. Here, the molecular mass are differing by 2. So here it is 108, so here it is 110. So the molecular mass of this compound in their isotopic form differ by 2. Now, here what is happening is, in case of chloro and bromo compounds, here the isotopic peaks will have the m by z value in the ratio 1:1. Now, if you take bromo compound here, so we'll have the molecules with one isotope of bromine 108. Other molecule can be an isotope with a bromine of atomic mass 110. So these two will show the parent peak. Now, these two parent peaks can differ at m by z value by 2. So here, if it is here at somewhere 108, here it will show at 110. So their parent peak will show at two different positions. So we'll have two parent peaks because of the two isotopes of bromine in the molecule. Now, if that is the case, in case of bromo compound, these two parent peaks will have the same intensity. Look at here. Here, this parent peak is for this compound with the bromine 108 atomic mass, and this will be another parent peak with the bromine atomic mass of 110. So they differ by 2. So we'll have two peaks here with the same intensity. So there are two parent peaks with same intensity. So if this kind of spectrum is being there in the spectrometer, if this is being analyzed, if this kind of spectrum is there, then we'll know that it is the bromo compound. If we are given a halogen compound and it is being analyzed, and if we get this kind of a spectrum, then we'll know that this spectrum belongs to the bromo compounds. In case of chloro compounds, if we take, for example, of ethyl chloride, this ethyl chloride can have a chlorine with one isotope of atomic mass 35. Then we can also have another chlorine atom in this molecule with atomic mass of 37. So still the compounds will differ their atomic mass by 2. So in that case also there will be two parent peaks being produced. So here the parent peaks they will differ m by z value by 2. The parent peaks here will be, the intensity of the parent peak will be in the ratio of 1:3. So in case of bromo compound, the parent peaks are in the ratio of, intensity of parent peaks are in the ratio of 1:1. But in the case of chloro compound, the intensity of the parent peaks are in the ratio 1:3. So if this is 1, if this is 1, this is 3. So their intensity differ, their ratio of intensity are in the ratio 1:3. So that's how we identify the halogen compound. So, bromo compound, same intensity parent compound, parent peak, but in chloro compound the parent peaks will have the intensity in the ratio 1:3. So, that is how we identify the compound from the mass spectrum. The compound of fluorine and iodine do not show M+2 peaks, as they do not have their isotopes. So, in case of chlorine and iodine iodo compounds, no such peaks, parent peaks will be produced. So, we can know that they neither belong to chloro compound nor belong to bromo compound, because these two atoms do not have their isotopes. If the mass spectrum does not contain molecular ion peak, the compound is either highly branched or is a tertiary alcohol. In some compounds, there are no parent peak being formed. So, in that case, we will have to know that the compound is either highly branched or it is a tertiary alcohol. For a straight chain alkane, fragment peaks are formed 14 units apart, and those base peak is due to C3H7 plus ion. So, if it is a straight chain alkane, we will have the fragments differing in their M/Z value by 14, and in those compounds the base peak will always be given by that fragment which has M/Z value of 43. So, this particular fragment will give in those alkanes, this particular fragment will give the signal with highest intensity. So, it will be taken as the base peak. It will also give additional M+1 peak due to isotope of carbon. In some cases, there will be also additional peak due to isotope of carbon. So, if it is a straight chain alkane, we can identify from the spectrum, we can identify from the base peak and how the fragments are differing. If the fragments are differing in terms of their M/Z value by 14 units, then we should know that yes, the compound is that of a straight chain alkane. For example, a compound forms a peak at, let us say, 100. So, we have a spectrum of a given compound, and the peaks formed are at M/Z value 100, 85, 71, 57 and 43. And in that spectrum, 43 is 100% intense, meaning, so 43 is giving the peak which is the base peak. So, how do we identify the compound now? So, from here we can deduce the molecular formula and also the fragmentation pattern of this compound. So, here how do we find that now? All the M/Z values of different fragments are given. So, if you look at here, the M/Z value of the fragments are nearly differing by 14 units. So, we have 100 here, 85 almost equal to 14, they differ almost by 14, and 85, 71 almost by 14 and so on. So, if you look at the M/Z value of different fragments and the molecular ion, they are differing by 14 units. So, from here we will have to make out that this compound could be an alkane, straight chain alkane. And also it is also saying that the fragment with M/Z value 43 is the base peak. Now, how do we deduce the structure of this compound now? Now, from here the highest, if you look at here, the highest M/Z value of the peak is 100 M. So, 100 is the parent peak. So, parent peak has the M/Z value equal to 100, which can be also the molecular mass of the compound. So, from here only we are able to know the molecular mass of the compound. So, the compound comes out to be the heptane. So, this is the compound which gives the above peaks with different M/Z values of the fragments. So, that is how we identify the compound. So, it is C7H16. So, that particular compound, let us look at how it undergoes fragmentation. So, these are the different fragments of heptane. So, this is the molecular ion of the compound heptane, and these are the different fragments or daughter ions and their M/Z values as shown by the spectrum. So, here this is the base peak which has M/Z value of 43. So, that is how we identify the compound from mass spectrum Now, if you have known the fragments and their m by z values, now can you draw the spectrum? You do it. On the y-axis, you draw the intensity. On x-axis, you draw the m by z value and draw different signals at different m by z value. So, try. Another one, write the formula for the fragments obtained from isobutane whose m by z values for the fragments are 43, 28 and 27 respectively. You can do this one as well. The m by z value of different fragments are given, which are 43, 28 and 27. So, from these m by z values, you can draw first, you can write the fragments, their formula, and then find out their formula looking at their m by z value. Now, let us look at the steps of analysis of sample by the mass spectrometer. In the first case, what is being done in mass spectrometry, what we do is there is ionization of the molecule by the bombardment of molecules by the electrons, highly energetic electrons. So, we have in the first case we have ionization. After that, we pass the ionized molecules through the electric field where they get accelerated, and then they are now passed to the magnetic field where they get deflected. Then after deflection, they are being detected. That is the steps which is involved in the mass spectrometer. Let us look at the instrument of mass spectroscopy. So, as I said earlier, so we have the sample here. This sample is being bombarded with highly energetic electrons. After that, they are being passed to the electric field, then they get accelerated, and after that they are being passed through the magnetic field. So, in the magnetic field, they get deflected at different angle depending on their m by z values. Then depending on their deflection, there will be detector and we will have the spectrum after that. So, that is how the mass spectrum is being produced in mass spectrometer. So, in the conclusion, let us look at what we have done today, what we discussed today. In today's lesson, we discussed about the principle of mass spectroscopy. We also discussed about how we illustrate mass spectrum. We also looked at instrumentation of mass spectrometry, and we also looked at some of the applications of mass spectroscopy. Now, you do the following questions. Just one question, you do it. An organic compound alkane shows the mass spectrum as shown on the right. So, we have this spectrum, mass spectrum given by mass spectrometer. An organic compound gives this kind of signal. So, from here, identify the base peak, identify the parent peak, also calculate the molecular mass of the compound, and finally, name the compound shown by this as indicated by this spectrum. So, with this, we have come to the end of our today's lesson. Thank you so much for watching. Thank you.